Because SSH provides administrative access, it is also one of the first services attackers target. If an attacker gains SSH access, they may be able to steal sensitive data, install malware, create unauthorized users, or take complete control of the server. To reduce these risks, organizations follow several industry-standard security controls. In this session, we will implement 3 essential SSH hardening measures. First, we will generate an SSH key pair. Instead of relying on passwords, we'll use cryptographic keys to authenticate users securely. This greatly reduces the risk of password guessing, password reuse, and brute force attacks. Next, after confirming that SSH key authentication works correctly, we will disable password-based login. This prevents attackers from attempting to log in using stolen or weak passwords.
In the previous lessons, we learned how SSH works, how Linux users are managed, and why secure remote administration is critical for Linux servers. Today, we're taking the next step by hardening SSH, which is one of the most important services running on any Linux server. SSH, or Secure Shell, is the primary method administrators use to remotely access and manage Linux systems. Whether it's an AWS EC2 instance, an Azure virtual machine, a Google Cloud VM, or an on-premises Linux server, SSH is the standard tool for secure remote administration.
Finally, we will disable direct root login over SSH. Rather than allowing the most privileged account to connect directly, administrators first log in using a standard user account and then use sudo when administrative privileges are required. This improves accountability, supports auditing, and follows the principle of least privilege. These are not just best practices for a home lab. They are common security controls used in production environments across cloud providers such as AWS, Microsoft Azure, and Google Cloud. Organizations implementing security frameworks like CIS benchmarks, ISO 27001, PCI DSS, and SOC 2 commonly recommend or require these controls as part of securing Linux servers. By the end of this session, our Ubuntu server will authenticate users with SSH keys, reject password-based SSH logins, and prevent direct root access, making it significantly more resistant to common attacks against remote administration services. Before generating a new SSH key pair, the first thing I want to do is check whether this user already has any existing SSH keys configured. In a production environment, we never assume that a server is in a clean state. As cloud security engineers, one of our responsibilities is to understand the current configuration before making any changes. If an SSH key already exists, it may belong to another administrator, an automation process like Ansible, or a previously configured deployment. Accidentally overwriting an existing key could cause administrators to lose remote access to the server. That's why our first step is always to inspect the SSH configuration, rather than immediately generating new keys. To do that, I'll run ls-la/tilde/.ssh.
Let me explain this command before executing it. The ls command lists files and directories. The -l option displays detailed information such as file permissions, ownership, size, and modification date. The -a option tells Linux to include hidden files and directories. The .ssh directory begins with a dot, which means it's hidden by default. Finally, ~/.ssh refers to the hidden SSH directory inside the current user's home directory. This is where Linux stores SSH keys and SSH-related configuration files for that specific user. Now I'll execute the command. As you can see, Linux returns the message, "No such file or directory." This tells us that the security admin user doesn't currently have an .ssh directory, which also means no SSH keys have been generated for this account yet. This is exactly what we expect, because this is a newly created administrator account.
Now that we've confirmed there are no existing SSH keys for this user, the next step is to generate a brand new SSH key pair. This is one of the most important security improvements we can make to a Linux server, because it moves us away from password-based authentication and toward cryptographic authentication. In most enterprise environments, administrators don't log into production servers using passwords. Instead, they authenticate using SSH keys. This approach significantly reduces the risk of brute force attacks, password guessing attacks, password reuse attacks, and credential theft. Before generating the key pair, let's quickly understand what we're creating. An SSH key pair consists of two keys. The first is a private key. This key must remain secret and should never be shared with anyone. The second is a public key. This key can be safely shared and will eventually be installed on the server. During authentication, the server verifies that we possess the matching private key without requiring us to send the private key across the network. This makes SSH key authentication significantly more secure than traditional passwords.
To generate the key pair, we'll use the SSH key generation utility called ssh-keygen. The command we'll run is ssh-keygen-t ed25519-c security admin at Linux Hardening Lab. Let's break this down before executing it. The SSH Keygen utility creates SSH key pairs. The -t option specifies the type of key we want to generate. In this case, we're using ed25519, which is a modern cryptographic algorithm that provides strong security and excellent performance. Today, ed25519 is widely recommended by security professionals and is commonly used across Linux servers, cloud environments, and DevOps platforms. The -c option adds a comment to the key. This doesn't affect security, but it helps identify who owns the key when managing multiple keys in an enterprise environment. Now let's execute the command. The first prompt asks where we want to save the key. Linux suggests a default location inside the .ssh directory in the current user's home directory. Since this is exactly where SSH expects to find keys, I'll simply press Enter to accept the default location. Next, Linux asks whether we want to protect the private key with a passphrase. A passphrase adds an additional layer of protection. Even if someone steals the private key file, they still need the passphrase to use it. In enterprise environments, using a passphrase is considered a security best practice. For this lab, you can either set a passphrase or leave it empty if you want to simplify testing. After confirming the passphrase, SSH generates the key pair and displays the key fingerprint and random art image. This confirms that the key pair was created successfully. Behind the scenes, Linux has also created the hidden .ssh directory that didn't exist earlier. Inside that directory, we now have a private key and a public key that we'll use in the next steps to enable SSH key authentication and eventually disable. We've successfully generated our SSH key pair. However, as a cloud security engineer, our job doesn't stop after running a command. We always verify what changes were made to the system. In this step, we're going to inspect the .ssh directory and understand every file that was created. This is an important habit in cybersecurity. Instead of assuming a command worked correctly, we validate the outcome and understand exactly what artifacts were generated. In enterprise environments, security engineers regularly inspect SSH keys while troubleshooting authentication issues, auditing user access, or investigating security incidents. To view the contents of the .ssh directory, I'll run the following command: ls-la/tilde/.ssh. This command lists all files, including hidden files, and displays detailed information such as permissions, ownership, and file sizes. After executing the command, we can see that Linux has automatically created the .ssh directory along with two important files. The first file is id_ed25519. This is the private key. It is your digital identity and must always remain secret. It should never be shared, uploaded to GitHub, or copied to another person. The second file is id_ed25519.pub. This is the public key. Unlike the private key, this file is designed to be shared with servers. In the next stage of our SSH hardening process, we'll copy this public key to the server so it can recognize and trust our client. You may also notice the file permissions. The private key has much more restrictive permissions than the public key. Linux protects the private key because it contains sensitive authentication material. From a security perspective, this separation is critical. The private key always stays with the client. The public key is copied to the server. During SSH authentication, the server verifies that we possess the matching private key without ever receiving the private key itself. This cryptographic approach is what makes SSH key authentication much more secure than traditional password-based authentication. Now that we've confirmed our keys were generated successfully and understand the purpose of each file, we're ready to install the public key on the server so we can authenticate without using a password.
So far, we've generated an SSH key pair and verified that both the private key and public key were created successfully. However, generating a key pair alone doesn't enable SSH key authentication. The server still doesn't know that this public key belongs to an authorized user. In this step, we'll register our public key with the SSH server. Think of it this way. We have created a digital identity, but we haven't told the server to trust it yet. To establish that trust, we need to copy our public key into a special file called authorized keys. This file acts as an access control list for SSH. Every public key stored inside it represents a user or device that is allowed to authenticate to the server. During an SSH login, the server checks this file. If it finds a matching public key and the client proves ownership of the corresponding private key, authentication succeeds. This is how SSH provides secure authentication without sending passwords or private keys across the network. In enterprise environments, every administrator, automation server, or CI/CD pipeline that requires SSH access has its public key registered in an authorized keys file or managed through a centralized access management solution. Before adding the key, let's first display the contents of our public key.
I'll run the following command: cat.id_ed2551952.pub. The cat command displays the contents of a file. In this case, we're viewing the public key, which is safe to display because it is specifically designed to be shared. After executing the command, you'll notice the key begins with ssh-ed2551952, followed by a long encoded string and the comment we provided during key generation. This entire line represents our public key. The next step is to copy this public key into the server's authorized keys file. Since we're configuring SSH for the same user on this Linux server, we'll first ensure the .ssh directory has the correct permissions. Then, we'll append the public key to the authorized keys file using the following command: cat.id_ed2551952.pub /.ssh/authorized_keys. Let me explain this command. The first cat reads the contents of the public key. The greater than operator appends that content to another file without overwriting existing entries. Finally, authorized_keys is the file that SSH checks whenever someone attempts to authenticate using an SSH key.
If the file doesn't already exist, Linux creates it automatically. After executing the command, our public key is officially registered with the SSH server. From this point onward, the server is capable of recognizing our private key during the authentication process. In the next step, we'll verify that everything is configured correctly and then test SSH key-based authentication before making any security changes, such as disabling password logins.
I'll run the following command: cat.id_ed2551952.pub. The cat command displays the contents of a file. In this case, we're viewing the public key, which is safe to display because it is specifically designed to be shared. After executing the command, you'll notice the key begins with ssh-ed2551952, followed by a long encoded string and the comment we provided during key generation. This entire line represents our public key. The next step is to copy this public key into the server's authorized keys file. Since we're configuring SSH for the same user on this Linux server, we'll first ensure the .ssh directory has the correct permissions. Then, we'll append the public key to the authorized keys file using the following command: cat./.ssh/id_ed2551952.pub /.
/authorized_keys. Let me explain this command. The first cat reads the contents of the public key. The greater than operator appends that content to another file without overwriting existing entries. Finally, authorized_keys is the file that SSH checks whenever someone attempts to authenticate using an SSH key.
If the file doesn't already exist, Linux creates it automatically. After executing the command, our public key is officially registered with the SSH server. From this point onward, the server is capable of recognizing our private key during the authentication process. In the next step, we'll verify that everything is configured correctly, and then test SSH key-based authentication before making any security changes, such as disabling password logins.
We have now generated our SSH key pair and registered the public key with the SSH server. However, in a security environment, we never assume that a configuration change works just because a command completed successfully. The next step is validation. Before disabling password authentication, we must confirm that SSH key-based authentication works correctly. This is an important security practice because if we disable password login before verifying key authentication, we could accidentally lock ourselves out of the server. In production environments, this validation step is part of a standard change management process. Security engineers first implement a stronger authentication method, test it, and only then remove the weaker authentication method. This follows the principle of maintaining availability while improving security. Now we will test SSH key authentication by creating a new SSH connection and forcing SSH to use our private key.
The SSH client will use our private key, ID_ED25519, and the server will verify it against the public key stored in authorized_keys. The authentication flow looks like this. Client: I want to authenticate using this private key. Server: I have this matching public key in authorized keys. Prove that you own the private key. Client: here is the cryptographic proof. Server: verification successful. Access granted. Notice that the private key never leaves the client machine. Now let's test the connection. So far, we've generated an SSH key pair and configured our Ubuntu server to trust our public key. However, before we disable password authentication, there's one very important step that we cannot skip. At the moment, the SSH key pair exists only inside our Ubuntu virtual machine. The private key is stored in the following location: /home/securityadmin/ID_ED255190. This creates an important question. If the private key is inside the Ubuntu server, how will my Windows computer authenticate to the server? The answer is simple. SSH authentication always happens from the client to the server. The client must possess the private key, while the server stores only the corresponding public key. This is one of the most important concepts to understand about SSH authentication. The private key never belongs on the server. It belongs on the administrator's workstation. The server should only know about the public key. Since we're connecting from Windows using PuTTY, our Windows machine needs a copy of the private key. Without it, PuTTY has no way to prove our identity after password authentication is disabled. If we skipped this step and immediately disabled password authentication, we would most likely lock ourselves out of the server. This is why production environments always validate SSH key authentication before removing password-based access.
The typical enterprise workflow looks like this. First, an administrator generates an SSH key pair on their workstation. The private key remains securely stored on the administrator's computer. Only the public key is copied to the Linux server. When the administrator connects through SSH, the client uses the private key to prove its identity, and the server verifies that identity using the stored public key. For learning purposes, we generated the SSH key pair directly on our Ubuntu server so we could understand how SSH keys work. Now we'll securely transfer the private key to our Windows machine so PuTTY can use it for authentication. The first step is to display the contents of the private key. I'll run the following command: cat///ID_ED255195. This command simply displays the contents of the private key file.
I'll carefully copy the entire key, including the beginning and ending lines. Next, I'll open PuttyGen on my Windows machine. Putty doesn't use the standard OpenSSH private key format directly. Instead, it stores private keys in its own .ppk format. Inside PuttyGen, I'll import the OpenSSH private key that we just copied. After importing it successfully, I'll save it as a Putty private key file with the .ppk extension.
Now I'll open the Putty session configuration. Under Connection, SSH, Auth, Credentials, I'll browse to the .ppk file and select it. Finally, I'll connect to the Ubuntu server again. If everything has been configured correctly, Putty should authenticate using the SSH key instead of asking for a password. Once this test succeeds, we know our SSH key authentication is working correctly. Only then is it safe to disable password authentication on the SSH server. This validation process is exactly how cloud security engineers perform SSH hardening in production environments. They never remove an existing authentication method until they have confirmed that the stronger authentication method is working successfully. Following this process helps prevent administrators from accidentally locking themselves out of production servers.
We've successfully configured SSH key authentication and verified that we can log in using our private key. Now it's time to remove the weaker authentication method from our SSH server. At the moment, our server supports two ways of authenticating users. The first is password authentication. The second is SSH key authentication. Even though SSH keys are configured, leaving password authentication enabled still allows attackers to attempt password-based attacks against our server. This means an attacker can continue trying weak passwords, stolen passwords, or automated brute force attacks until they either succeed or are blocked. As cloud security engineers, our goal is to reduce the attack surface. Rather than trying to protect a weaker authentication method, we remove it completely. This is a common security control implemented on production Linux servers running in AWS, Microsoft Azure, Google Cloud, and enterprise data centers. Before making any configuration changes, we'll first create a backup of the SSH server configuration. This is an important operational practice because it allows us to quickly restore the previous configuration if something goes wrong.
I'll create the backup using the following command: sudo cp/etc/ssh/ etc/sshed_config/etc/sshed_config.backup. Next, I'll open the SSH server configuration file, sudo nano/etc/ssh/sshd_config. Inside this file, I'll locate the password authentication directive. Depending on your Ubuntu version, it may already exist or it may be commented out. If it's commented, I'll remove the comment. Then I'll change the value to password authentication no. This tells the SSH server to reject all password-based login attempts. From this point onward, users must authenticate using an approved method, such as SSH keys. After making the change, I'll save the file by pressing Ctrl+O, press Enter, and then exit Nano using Ctrl+X. Before restarting the SSH service, it's a good practice to verify that our configuration doesn't contain any syntax errors. I'll run the following command: sudo sshd-t. If the command returns no output, it means the configuration is valid. Finally, I'll restart the SSH service so the new configuration takes effect.
Sudo systemctl restart SSH. To verify the change, I'll open a new Putty session. Since password authentication has been disabled, the server should authenticate me using my SSH key. If I remove the private key from Putty and try connecting again, the login should fail because password authentication is no longer allowed. This confirms that the server now accepts only SSH key-based authentication. In this lecture, We strengthened our Linux server security by implementing SSH key-based authentication and preparing our server to remove password-based access. We learned how SSH keys improve security, reduce brute force risks, and follow enterprise authentication practices. In the next lecture, we will continue SSH hardening by disabling direct root login and implementing stronger privilege management. See you in the next part of the Linux server hardening project.